Hi, everyone. Thank you all for coming. This is some work that I've been working on with my advisor first of all, my name is Aisha Khatib. I'm a graduate student at the University of Maryland. And this is some work that I have been working on with my PhD advisor, Nick Schmer, and my committee members, Vad Lekic and Renee Weber. And this is somewhere where I am trying to apply a new analysis technique to a very old set of data. So to get started, I wanted to give a brief background onto what deep moonquakes are, where they came from. And their story really starts with the Apollo Lunar Surface Experiment Package, which are the 5 seismic stations which were placed during the Apollo missions between 1969 and 1972. They recorded continuously until 1977, so we have 5 to 8 years of seismic data on the lunar near side. Over 12,000 events have been identified in the seismic record, more than half of which are deep moonquakes. And deep moonquakes are repeated seismic events that are hypothesized to be from kilometer scale source regions, mainly on the lunar near side, that occur at focal depths between 700 kilometers and 1,200 kilometers. The events that we have were identified mainly through waveform stacking and then cross-correlation through the entire seismic record. And the question that I'm really trying to answer with this new analysis technique is, what is the focal mechanism behind these deep moonquakes? And how much can we trust the assumption that each cluster or nest propagates identical moonquakes or identical seismic events? The study that I am presenting today focused specifically on the A1 deep moonquake cluster. This is the largest deep moonquake cluster in the seismic record. It's approximately 970 kilometers southwest of Apollo 12. I will specifically be looking at detections at Apollo 12, just because it was the longest one it was the longest station on the surface and detected the most events. And I have some examples of the 443 events in this deep moonquake cluster. And as you can see, they're not very similar. They're similar, but they're not identical. There are changes in waveform shape, in rise time, in signal to noise ratio, in artifacts like bit swaps and glitches. So there are a lot of variations even within one cluster. So the method that I'm going to be using is called wavelet scattering transform. And this is a type of unsupervised machine learning technique in which an input signal is convolved with a family of wavelets. And that wavelet, this wavelet family is usually one wavelet which is stretched, compressed, and rotated so that it spans all of frequency space. And what this does is it helps yield a compact set of coefficients of the original data that really isolates the defining characteristics of that data. This is a really powerful technique. It's fairly new. It's been able to classify audio signals before, and it has recently, in a study by Chung et al. In 2020, been able to differentiate between different cosmology fields, even when their power spectra are virtually indistinguishable. So this was something that I really wanted to use on Apollo data of deep moonquakes. So this is just a visualization of my data. These are the envelope of all 443 A1 deep moonquake events. So from left to right, it's the Z component, the first component, and the second component, because we have 3 components on our seismometer. And on the x-axis, you have samples. So we cut them to all the same sample length, 1,600 samples, which is about 40 minutes. And your event index is on the y-axis. And as you can see, there are differences in length and intensity in the same cluster. The only pre-processing that I've done is I removed any events that had obvious differences in signal, for example, periodicities that were associated with maybe instrument glitches, the arrival of any secondary events, and any flat time series that was also probably due to an instrument glitch. So this is a visualization of the scattering coefficients after I perform the scattering transform. Again, you have your scattering coefficients on the x-axis of your right diagram, and then on the y-axis, you have your event index. And the first value you see is the 0th order coefficient, and that's just the average of your original time series. So that there's not a lot of information gained here. The first order, which is your next set of coefficients, is comparable to your power spectrum. And that's the first convolution and kind of average of a set of wavelets to your original time series. But where a lot of the information lies is in the second order. And this shows where your packets of energy are clustered. And this is because you are doing a second order of wavelet convolutions on your first order coefficients. So this not only shows you where there is energy, at what frequencies there is energy, but at what time scales, at what length scales these energy packets come in. So I visualize this by kind of cutting out the 0th and the first order, and we're focusing specifically on your second order because that gives us the most amount of information. So this is the Z component, this is the first component, this is the second component. There are similarities in pattern for all 3 of these components. The next thing I wanted to do was to sort these scattering coefficients to see what groups kind of pop out. And the way I did this was using T-distributed stochastic neighbor embedding, or TISNE. And what this does is it reduces your scattering coefficients down to 3 dimensions, basically. And what you can do with that is you can calculate distances between each of these separate points. And that helps you sort the scattering coefficients of each time series based off of similarity. And what we're seeing is basically a stratification into very specific groups. And for the rest of this talk, I'm going to go through the kinds of groups that we're seeing in the A1 deep Moonquake cluster. Just to stay oriented, I am on the left, I am highlighting the group that I'm kind of talking about. And then on the right is a one-dimensional plot of the second order scattering coefficients, as well as the time series of an example event that we found. So the first subgroup are glitchy events. And this is where you see large coefficients for the earlier scales in your second order scattering coefficients. And what these are associated with when we look at the time series are large amplitude spikes. And what we hypothesize these spikes are from something different from deep moonquakes. It's either instrument movement, especially because a lot of these spikes are hitting the dynamic range of the instrument. So that's something that that pops out quite clearly. The second event has these high values for large coefficients at the higher scales, which are also kind of pointed out with these anomalous spikes right here. Thank you. What this kind of, when the scales are very high, it usually means that the time scales are very, very short. And this indicates small packets of high frequency energy. And when we look at the time series for these, we are seeing bit swap. So basically these tiny portions in the time series where the seismic data is basically wobbling above and then below zero, excuse me. The next subgroup is kind of dispersed throughout the seismic data, and it's high signal to noise versus low signal to noise. And I've demonstrated this with 2 example time series. The blue is very high signal to noise, the yellow is very low signal to noise, and doesn't have that characteristic deep moonquake shape. And so what we're seeing is for events that have high signal to noise ratios, there are spikes at the later coefficients for each scale at the second order, which are not present for low signal to noise events. The last subgroup, and maybe the most interesting, is one that I've called gradient, and it is highlighted at the bottom half of my left figure. And here, the coefficients at the 4th scale vary from small to large. And this is really preliminary results, but we don't exactly know why they're doing this because the differences in the time series are really difficult to spot. We don't know what they are. There are hypothetical causes, differences in rise time, differences in decay time, but we're not seeing those in the examples in the studies that we're in the events that we're seeing. So despite this, these groups exist on all 3 components of the Apollo 12 seismometer. The ones that I was showing you were the Z component, but we're also seeing them on the first component and the second component. They have similar numbers across components, but they don't necessarily overlap exactly. I will skip this considering I am already over time, but I will add a summary slide and just say that this process could be expanded out and will be expanded out to other deep moonquake clusters, not just the A1 deep moonquake cluster. And this could be used to regroup the existing deep moonquake events and find new ones in the Apollo seismic data. And with that, I will stop because I am very over time. Thank you so much. Oh, great. Thank you so much for your attention.